All right, in the previous lecture, we talked about electronic orbitals and what they are. An orbital is a place that we can house an electron. So an orbital is a location, or you can kind of consider it an electron home. It's where the electrons are placed. Now, each orbital will take up to 2 electrons to fill it. And once an orbital is full, we have to then go to the next orbital. And what we're really doing here, as I said before in the previous lecture, if I've got my nucleus, it's how many electrons am I putting on each of those energy levels. Okay, you can conceptually think of it as rings around the nucleus before it's full and we have to fill up our next energy level. Okay, and the number of orbitals that exist in each of those energy levels, that will dictate how many electrons it takes to fill that ring. Okay. Now, these orbitals have specific names and numbers associated with them, and those are dictated right here. And for those that watch the video, okay, the numbers out in front tell me what energy level. So 1s, the one out in front, tells me or corresponds to the first ring around the nucleus. So there's only one orbital that's found on the first floor. The second floor, 2s and 2p, those are the only 2 orbitals that are found on the second ring. On the third ring, there are 3 different orbital shapes. On the fourth ring, there are 4, and after the fourth ring, all of the other rings just simply follow the fourth ring. So once we get to floor 4, all of the subsequent floors after that, rings, are exactly the same for floors 4, 5, 6, and 7. Okay? Now, each of these orbitals will take up 2 electrons to fill it. All right? And with that, we can number these in this order that I have here, and there's something called the diagonal trick, which is a quick way of memorizing which sequence of orbitals are filled. Now, this used to be a technique I would have my students because one of the goals that students had to do is to memorize the sequence. What orbitals do we fill first, and who do we fill next, and who do we fill next? Because of the fact of the test being taken at home, what I expect most of you to do is to just simply write down the order of which they fill. All right? So the first orbital that we fill is the 1s. Once that is full, the first floor is full. The first ring is full of electrons. And this is why only 2 electrons fill the first floor, because it only takes 2 electrons to fill that orbital. Once it's full, we move up to the next orbital, which would be the second floor, and the first orbital we fill is also an s. You'll notice on every floor there's a single s orbital. Once we fill the 2s, we then fill the 2p. Now again, the s orbital looks like a sphere, like a tennis ball or a golf ball. P orbitals look almost like dumbbell orbitals. Spherical orbitals look like circles, but in 3 dimensions. Once we fill the 2p orbitals, and again, what you have to remember from the lecture is that there are 3 2p orbitals. Specifically, it's called 2px, 2py, and 2pz, because there is a dumbbell located along the x-axis, along the y-axis, and a z-axis. So p orbitals always come in triples. So what you have to remember for the test is that the 2p orbital, any p orbital, there are 3 of them. So there are a total of 4 orbitals on the second floor. So when we are in the second floor, we have the 2s to fill, the 2px to fill, the 2py to fill, and 2pz to fill. Because there are 4 orbitals to fill on this second floor, each one takes 2 electrons to fill each. That accounts for 8 electrons. So it takes 8 electrons to fill the second floor. Now, if you look at your periodic table, the first row, the first horizontal row, contains just hydrogen and helium. Helium has 2 electrons. Once we have 2 electrons, the first floor is filled, and the first floor on the periodic table is in conjunction to the rings around the nucleus. And that's why only 2 electrons fill it, and that's why there's also only 2 elements on the second floor. On the first floor. On the second floor, the lithium floor, floor 2, this horizontal row, 8 electrons fill it, and you'll notice that the element neon concludes the second row of the periodic table. Neon has got 10 electrons with it. Well, the first 2 electrons fill the first floor, the next 8 electrons fill the second floor. Neon finalizes and finishes the second floor of the periodic table because the second floor now is completely full. Now if we have more electrons, we move up to the third floor, and now we fill the 3s, the 3p. Okay, and then you would predict that the 3d would fill next. But if you look at the periodic table, the third floor also contains only 8 more electrons. Why is that? And the reason has to do with energy. What happens is it is found out that once we start getting to bigger and bigger elements, these energies of these orbitals tend to get very close to each other. And it's found that the 4s orbital fills before the 3d. Okay? So this right here is a key thing to memorize for the test. Once we fill the 3p, we don't fill the final 3d. We actually jump up and fill the 4s and then come back down and fill the 3d. After the 3d, then we fill the 4p. Okay, and then we would go to 5s, 4d, oops, my bad, d, I'll back that up, and 5p. For the test, you only have to memorize up to 4p. So what I would do, and what most of you probably will do, is you'll write down 1s, 2s, 2p, 3s, 3p, 4s, 3d, and 4p. This is the order which we fill electrons. And you're only going to be expected to be able to do the electron configurations for the elements hydrogen through krypton, number 36. Once we get past krypton, we start filling then higher orbitals, which the diagonal trick will tell us what orbitals fill in what order, but for the sake of this test, this is the only order that you have to know. Now, if we only need to use up to 2p to fill all the electrons that an element has, fine, we're done. But this is the farthest we'll get in electron configurations for the exam. Okay? So how the diagonal trick works, if you're wondering, is I draw a diagonal line and we'll fill, the 1s orbital fills first because I crossed it out first. The next diagonal line, we fill 2s. The next diagonal line, we fill 2p, and then we fill 3s. The next diagonal line, we fill 3p, 4s. And that's how we're able to get the 4s before we do the next diagonal line and get 3d, 4p, and 5s. 4d, 5p, 6s. 4f, 5d, 6p, 7s, and so on and so forth. And that's how we get all the elements all the way to number 118, which we currently have on the periodic table. But you only have to remember up to 4p. Once you get to 4p, stop. Okay? Now, once you have the order filled, what we're doing here is called Aufbau's principle. Aufbau says that when we put electrons into orbitals, we fill the lowest energy orbital first before we fill the next one. The 1s orbital is less energetic than the 2s. Electrons in the 1s orbital are the lowest energy electrons. Once they're filled, we go up to the 2s. The 2s orbital is less energetic than the 2p. The 2p is less energetic than the 3s. The 3p is less energetic than the 4s, and so on and so forth. So we fill the lowest energy orbital. Once it's full, we go to the next orbital. Pauli exclusion principle states that when you have 2 electrons in the same orbital, they have to spin in opposite directions. So here we see different ways that we can designate orbitals. Sometimes you see a textbook do it as a circle. That circle might be, for example, the orbital 1s. 1/ indicates an electron, and if you think of like algebra, this would have a positive slope associated to it. This would have a negative. What this is relating back to is on that previous lecture is that when I have 2 electrons in the same orbital, one electron spins one direction, the other electron spins the other direction, so that they can stay in the same orbital and not repel each other immensely. So Pauli says that we put 2 electrons in the same orbital, they have to be in opposite spin states. The way that we will symbolize these orbitals is flat lines. And when we put 2 electrons in the same orbital, the arrows have to be up and down. What we cannot do is to have two arrows both be up. This is a violation of Pauli exclusion principle. So when you have two electrons in the same orbital, they have to spin in opposite directions. Okay? The last one is called Hund's rule. Hund's rule states that when we have an orbital of equal energy, they have the same sublevel, we have to put one in each before we double up. So an example of this would be the 2p orbitals. Because when I have the 2p orbitals, I have 2px, 2py, and 2pz. Each orbital can only take two electrons, but we have to put one electron in each before we can double up. What we can't do, Hund says, is fill 2px before we fill 2py. Because the 2px orbital, 2py orbital, and 2pz orbitals, because they're all 2p orbitals, they all have the same energy because they are the same floor, second floor, and they have the same basic shape. The only difference between a 2px and a 2py orbital is their orientation in space. One is located along the x-axis and one is along the y-axis. So when we fill atomic orbitals, Hund says we put one in each before we come back and double up. Those are the rules to filling atomic orbitals. Now, some of you might be totally lost right now. That's fine. We're going to do examples of this, and what you're going to find out very quickly is it's just a sequence. Once you get the sequence down, it's pretty simple. All right, so if you turn the page, well, first, whenever we do orbital notation, the orbital we always put down first is 1s. To over here, there are two exceptions that you have to memorize that occur in the first 36 elements from hydrogen and krypton. You're only going to be tested on the first 36 elements in this unit. You are not expected to do configurations of elements beyond number 36 krypton. Within those first 36 elements, there's only two elements that violate the sequencing of filling in the order that you expect. Copper is one of them. Instead of being 3d2, 4p, Instead of being 4s2, 3d9, one of the electrons goes into the 3d to fill it and to completely fill the third floor. Now some might ask why. Why do the last two electrons do this? Everything that explains why is always answered with energy. It's less energetic to fill the 3d orbital completely full than to have the 4s full versus the 3d being 9 out of the 10 electrons. So this is the configuration that copper has. Chromium, if you were to do the normal configuration, chromium has got, let's check here, 24 electrons. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6. Okay, and after 3p, 4s2, 3d4. This is the expected configuration that I would expect you to think chromium would do if you filled it in perfect order. But instead, what happens, just like copper, is that one of the electrons in the 4s jumps into the 3d. This one's a little bit easier, I think, for students to understand, because if you look at the last two orbitals, you got to remember the 3d orbitals, it comes in quintuplets. There are 5 of them. Well, if you look at what the first state, if it was 4s2, 3d4, this is what it would look like in the orbital notation for the last two orbitals. I'm not writing the first 1s through 3p. But you'll notice that there's a 5th vacant orbital for 3d. And you can see why it would make sense that maybe one of these electrons would jump over here, because now I'm able to not have as much electron repulsion. Because there's a vacant orbital sitting there, if I throw one of the electrons up into there, that little bit less of repulsion is minimized, and this is the preferred configuration for chromium. Okay, so in your packet you have this page, and what we are going to do is do the orbital diagram for the following elements. Okay, we're going to start off with the easiest one, and we're just going to get more complex. So hydrogen, the first thing you got to do is figure out the number of electrons it has. Well, if you remember, The atomic number of hydrogen is 1. The atomic number gives you the number of protons. These are all atoms. So when we have an atom, the number of protons equals the number of electrons. So the number of electrons will basically be the atomic number of the element. So hydrogen has 1 electron. Okay? What orbital does it's the only orbital on the first floor. So I'll put a line. That line denotes the orbital, the home that the electron is in. And we write down below it what orbital that is. 1s means it's on the first floor, the first ring around the nucleus, closest to the nucleus. And the s tells me it's a spherical orbital. I have 1 electron, so I can put a single arrow indicates a single electron in the 1s. That is the orbital diagram of hydrogen. That's it. Or you could have done 1s and you could have drawn the arrow down. It doesn't matter which way the arrow is. You just have to make sure that it's one or the other. 1 arrow in the 1s means that we have 1 electron in the 1s orbital. And that's all there is to it. That is the orbital diagram of hydrogen. Helium has got 2 electrons. Which orbital do we put electrons in first? Always 1s. 1 arrow denotes 1 electron, and now we have the second electron. When I put the second electron in this orbital, the orbital will be full. What's the only thing I can't do with that second arrow? And hopefully you said not to have it also be arrow up. That would be incorrect. That is a violation of Pauli exclusion principle. So what we have to do instead is put the second arrow as spin down. So whenever we have 2 arrows in the same orbital, 1 is up and 1 is down. That's all you have to remember. Right there is the orbital diagram for helium. Okay, let's keep moving on. Lithium has got 3. The first orbital we always fill is 1s. How many electrons fill the 1s? Hopefully you said 2. Now we have 1 more electron to account for. So once the first floor is filled, we now have to go to the next orbital, which is 1 step higher in energy. And which orbital is that? The 2s. We are now starting to put electrons on the second floor, which if you think of the periodic table, hydrogen and helium, that's the first floor. Now we are starting to put electrons in the second floor of the periodic table, which should hopefully make sense to you. 1 arrow, the arrow could be either up or down, it doesn't matter, but there is the orbital diagram of lithium. Okay, carbon, we're going to jump past a few elements. Carbon's got 6. Again, the first orbital we fill is 1s. The next orbital we fill is 2s. Again, each line can only take up to 2 electrons and we're full. After we get to the 2s, who do we fill next? Not 3s. There's another orbital, which is the 2p orbital. Now, this is the tricky part. You have to remember that the 2p orbitals always come in triplets because there's an x, y, and z orientation. Now, Hund's rule states we have 4 electrons accounted for. We need 2 more. What we have to do now, what we cannot do, is put both electrons in the same orbital for 2p. That is a violation of Hund's rule. So what do we have to do instead? We have to put another electron in any of the other 2 orbitals. It doesn't matter. I could put an electron in a 2pz. Great. You could put it in the 2py. You could have them be 1 up, 1 down. It doesn't matter. But what you have to do is you have to make sure that there's 2 electrons in 3 of the 2p orbitals. And right there is the orbital diagram of carbon. One question you might ask is, Mr. K, if I don't have an electron in an orbital, do I still have to show it? Yes, because we have some electrons already in the 2p, we must show all of the potential orbitals those electrons could be in. Because what I've drawn here is one possibility, but there potentially could be 4 or 5 different possibilities and combinations. We're just showing you one of those. Okay? Now what I'd like you to do now is to pause the lecture and try to do the remaining elements and then restart the lecture, and I'll have the answers posted because I'm going to pause it myself and complete these elements and see if you get the same answers as you're checking through. Okay, so pause the lecture now. All right, so if you've completed the elements that I've told you to go ahead and do, I had you go ahead and do oxygen, I think was the first one. And with oxygen, there's 8 electrons. So you should have 2 electrons in one of the 2 p's. It doesn't matter if it's X, Y, or Z, but I always usually work left to right. Boring that way, but that's the way it is. And there should be 2 single electrons in 2 of the other 2p orbitals. Neon has got 10 electrons, and it fills the 1s, the 2s, and all 3 2p orbitals. And now we have filled the second floor, and that's why neon again is a noble gas. You'll start noticing a common theme. The noble gases will always completely fill the floor that they are on. So because that floor is completely filled, that floor is full of electrons, and therefore noble gases aren't very reactive because all of their floors are completely filled with electrons. Why elements react is because they are not filled in their valence or their outermost shell, which we'll talk about in the next lecture. So you're going to start to notice elements that are in the same period or same vertical family tend to have very similar configurations for their last electron location. Okay. Sodium, once we get past 10 electrons, we now jump to the third floor. So you should have now 3s for the first time. And we get a single arrow, could be either up or down, doesn't matter. Silicon, we get the 14 electrons, so now the 3s orbital is full, and now we start filling the 3p, and we fill the 3p just like the 2p. We put 1 in each before we start doubling up. So sulfur, we have 2 electrons, so 1 of the 3p's is completely filled. 2 of them are half filled. We need 2 more electrons to fill it, which then occurs in argon, where now all of the electrons, all of the orbitals, 1s, 2s, 2p, 3s, and 3p are completely filled, and again we reach the next noble gas. Potassium, this is that oddity that we fill after the 3p, we fill the 4s before the 3d. And so now we get the 4s orbital for the first time with a single electron in it. So what you've done here is called orbital diagrams. They're the most complex. They give you the fullest picture of the electron configurations, but as you can see, they take a lot of time with all these arrows. So there's a quicker way of doing that, and if you turn the page, what is this all? That quicker way is called electron configurations. So instead of arrows, so for example, with the element lithium, the orbital diagram was 1s2 and 2s1 like this. To go faster, instead of doing the arrows, scientists created a shorthand version of it, which is what you're going to see more often on the test. Instead of doing all these arrows, they simply write the orbital 1s, and because there's 2 electrons in it, we just simply say 1s2. 2s has got 1 electron in it, so we say 2s1. Okay? If you do something like carbon that has 1s, 2s, 2px, 2py, and 2pz has nothing in it. What we do is we group all of the equal energy orbitals. If they have the same first number and first letter, 2p, 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 we group them all together. So the orbital diagram for carbon, the electron configuration for carbon will be 1s2, 2s2, and 2p2. Okay? So that's how we do electron configurations. So let's look at, for example, the element iron. We look up the element iron, Fe. It has 26 electrons. All right, so what's the first orbital we fill? 1s, 2. Next one we fill is 2s, 2. Next orbital we fill is 2p, and we don't split them up as x, y, and z because this is a short version. It's a simplified version. So what you have to remember is the biggest number on an S will always be 2. Once we get to 2, it's full. P, because we group X, Y, and Z together, P will take up to 6 electrons to fill it in electron configurations. D, they come in sets of 5, 2 electrons in each, so a D will take up to 10 electrons, and you won't have to worry about Fs, but you do if you're in AP chemistry, because they come in groups of 7, and F will take up to 14 electrons. So these are the max numbers. You will never see there be a P with a 7 on it. That is incorrect. Once we get to 6 electrons, we have filled the X, the PX, the PY, and the PZ. So iron is 2p6. Now if I count up the superscripts, 2 plus 2 plus 6, that adds up to 10 electrons. So the subscripts, if you add them up, that will add up to the number of electrons in the element. So who do we fill after 2p? 3s. Again, it's an S, so it'll take up to 2 electrons. That gives me 12. 3p will take up another 6. That gets me to 18. Now, who do we fill after 3p? 4s. That takes another 2. That gets me to 20. And then after 4s, we come back and fill the 3d. Now remember, a d will take you up to 10 electrons, but currently we have 20. I only need 6 more. So all I got to do is say 3d6. Okay? All right, let's look at magnesium. Magnesium's got 12 electrons. If you want to pause the lecture now and see if you get it right, please do. All right, 1s, 2, 2s2, 2p6, 3s2. 2 plus 2 plus 6 plus 2, that adds up to 12. Magnesium's got 12 electrons. There is the electron configuration for magnesium. So really the kicker here is you just have to memorize the sequence and memorize what's the max number in all the orbitals. And if you got the sequence down to the max numbers, you can do the electron configuration for any element. Okay? Once an orbital is full, we move on to the next one. And that's all it is. It's basically a sequence. And if you've got your sequencing down, this is a pretty simple concept. All right, copper has got 29 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. If you were to fill it in perfect order, maxing out the S to a 2, maxing out the P to a 6, and eventually getting to 3D, we are 1 away from filling it, we get 3D9. This is the expected configuration for copper, except now there's trouble that pops up. Some of these elements do not follow in a perfect sequence. We call these exceptions elements. Copper is an example of an exception element. What happens instead is one of the electrons in the 4s goes and fills the 3d. So if I go back, in the end being, copper and chromium are the 2 exceptions. And yes, because these are take-home tests, you literally could write those down, and if it's on the test, you've got the answer supplied to you. But I'm hoping, again, for some of you, you're going to want to just try to do the class without that crutch. But that is, again, something just to realize. So for the first 36 elements, there's only 2 exceptions, copper and chromium. Okay? All right, let's look at krypton. Krypton is the biggest element. It's got 36 electrons. It's the biggest configuration you're going to be expected to have on the test. 1s2, 2s2, 2p6. After 2p, who fills next? 3s, 3p. Who fills after 3p? 4s. Then comes 3d. What's the max number on a d? 10. That gets me up to 30 electrons. Who fills after 3d? 4p. A p again will take up to 6. And if we look at that, that gets me 36 electrons. And again, like all noble gases, we end with a completely filled p orbital. And that's true for all the noble gases except for helium, because there is no 1p orbital. Once we fill the 1s, it is completely full. All right, so again, pause the lecture and try to do the rest of the elements, doing electron configurations, to see how well you're understanding this concept. All right, so finishing these elements up, starting with chlorine. Chlorine's got 17 electrons, 1s2, 2s2, 2p6, 3s2, 3p5. So one little thing to kind of think about, another type of test question I could ask you is I could say, okay, an element has a configuration of 1s2, 2s2, 2p4. Which element is this? Okay? How would you attack that problem? What would you need to do to solve the answer? hopefully you're thinking to yourself, well, if I add up the number of superscripts, that will equal the number of electrons. Okay? And if it's an atom, the number of protons must be the same. So which element has got 8 protons? The element is oxygen. So if you are given electron configuration of an atom, you should be able to easily figure out what the element is based off of its electron configuration. So that's another style of question that you're going to see both in the quiz for next week and also the test. Okay? Nitrogen, 1s2, 2s2, 2p3. Phosphorus, 1s2, 2s2, 2p6, 3s2, 3p3. Arsenic, 1s2, 2s2, 2p6, 3s2, 3p6, F4s2, 3d10, 4p3. Zinc, very much like arsenic, except there's no 4p3, 30 electrons. Fluorine has got 9, 1s2, 2s2, 2p5. And calcium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now at first, I understand this concept can be a little bit difficult to get, but once it clicks, it's like riding a bike. Once you understand that it's simply a sequence, and if you memorize or know the number of electrons that will fill an orbital, it's all a matter of filling an orbital and moving to the next one and filling it until you've got all the electrons accounted for. And that's really all there is to it. Okay, next week we'll then finish off and talk about these last 4 columns, which you don't have to worry about today. There's a homework assignment which goes over some more elements on these configurations that I'd like you to try for practice. And then next week you'll have a short quiz. You'll actually have 2 of them. You'll have one quiz on nuclear decay, and you'll have one quiz on electron configurations, just to test your understanding before we get into the test, which will be then the following week. So we're about still 2 weeks out, but these are the final types of concepts you have to be aware of and have mastery of leading into that second to last quiz, a test for quarter 1. Okay, again, if you have any questions, don't be afraid to get a hold of me.